Have you ever wondered how a tiny drop of water can dissolve an entire spoon of salt? Or how ammonia, with its strong pungent smell, is used to clean greasy kitchen surfaces? Both of these everyday substances, water and ammonia, owe their remarkable properties to something fundamental in chemistry: covalent bonding. In covalent bonding, atoms do not transfer electrons as in ionic bonding. Instead, they share electrons to achieve stable electronic configurations, just like noble gases. Water and ammonia are excellent examples of polar covalent compounds where the sharing isn't equal, and that makes these molecules behave in fascinating ways. In today's video, we'll explore how these molecules form, how they're represented using electron dot and orbital diagrams, and why their shapes matter in real world chemistry. Let's begin with the most familiar molecule, water. A hydrogen atom has one electron. To become stable like helium, it needs one more electron to complete its duplet, that is, two electrons in its outermost shell. Oxygen has an atomic number of 8 with an electronic configuration of 2, 6. It needs two more electrons to complete its octet, or 8 electrons in its valence shell, just like neon. So, in a water molecule, each hydrogen shares one electron with oxygen, and oxygen shares one electron with each hydrogen. That's how both hydrogen atoms reach their duplet, and oxygen reaches its octet. This results in the formation of two single covalent bonds, one between each hydrogen and the oxygen atom. The final molecule of water, chemically written as H2O, is not linear. It's bent in shape due to lone pairs on the oxygen atom, making it a polar molecule. Let's now look at the electron dot structure of a water molecule. Before bonding, each hydrogen atom has one valence electron, shown as a single dot. The oxygen atom has 6 valence electrons, with two unpaired electrons ready to form bonds. When the atoms combine, each hydrogen shares its one dot with one of oxygen's unpaired electrons. These shared pairs form two single covalent bonds, one between hydrogen and oxygen on each side. The oxygen atom also has two lone pairs of electrons. These are not involved in bonding but influence the bent shape of the water molecule. So the electron dot structure of water shows oxygen at the center, bonded to two hydrogen atoms, with two lone pairs remaining on the oxygen atom. Chemical formula: H2O electron dot format, H single bond O single bond H with two lone pairs on oxygen. Let's go a step deeper with the orbital representation of water. The oxygen atom has 6 valence electrons. Two of these are shared with the single electrons from each hydrogen atom, forming two overlapping orbitals which represent the two covalent bonds. The other 4 electrons remain as two lone pairs, occupying space and pushing the bond pairs closer together, creating a bent or angular shape. This angular shape is responsible for the polarity of water. Oxygen pulls shared electrons slightly more towards itself, giving it a partial negative charge, while the hydrogen atoms carry partial positive charges. Visual cue: on the screen, observe the orbital diagram of the water molecule, two shared orbitals forming bonds and two lone pairs remaining on oxygen. Let's now turn our attention to ammonia with the chemical formula NH3. Nitrogen has an atomic number of 7. Its electronic configuration is 2, 5, meaning it needs 3 more electrons to complete its octet. Hydrogen again has 1 electron and needs 1 more to reach its duplet. So nitrogen shares 1 electron each with 3 hydrogen atoms, forming 3 single covalent bonds. In doing so, nitrogen achieves a full octet and each hydrogen gets a duplet. Now, nitrogen originally had 5 valence electrons and it only uses 3 of them to form bonds. The remaining 2 electrons stay as a lone pair on nitrogen. This lone pair is important. It pushes the bonded atoms downward, creating a trigonal pyramidal shape, not flat. This shape makes ammonia a polar molecule just like water. Let's now draw the electron dot structure of ammonia. Before bonding, nitrogen is shown with 5 dots, 3 unpaired and 1 lone pair, and each hydrogen with 1 dot. When bonding occurs, each hydrogen shares its 1 electron with nitrogen's unpaired electrons. This forms 3 single covalent bonds, one between nitrogen and each hydrogen. After bonding, nitrogen has 3 shared pairs and 1 lone pair of electrons. This lone pair causes electronic repulsion, giving the molecule its pyramidal shape. Chemical formula: NH3 electron dot format, nitrogen at the center, single bond to each hydrogen, and 1 lone pair above nitrogen. Let's now bring it all together. Water, with the formula H2O, has 2 single covalent bonds and 2 lone pairs on oxygen. Its bend shape and polarity explain its excellent solvent power and high boiling point. Ammonia, written as NH3, has 3 single covalent bonds and 1 lone pair on nitrogen. Its trigonal pyramidal structure and polarity make it a strong base and an important industrial compound. Both water and ammonia are polar covalent compounds, molecules where electrons are shared but not equally. That unequal sharing gives rise to partial charges, leading to real-world properties like solubility, boiling point, and reactivity. So to summarize, covalent bonds are formed by sharing electrons. Water and ammonia both contain single covalent bonds. Their lone pairs influence their shape and polarity. These molecules play vital roles, from hydration in your body to cleaning agents in your home. I hope this session helped you understand how simple elements like hydrogen, oxygen, and nitrogen come together to form the very molecules that surround us every day. In the next video, we'll take this idea one step further as we explore coordinate bonding, where a single atom donates both electrons in a bond. We'll specifically look at how hydronium ion, written as H3O positive, and ammonium ion, written as NH4 positive, are formed. So stay curious, and I'll see you in the next session with the fascinating chemistry of coordinate bonds.